Okay, examples and practice. Let's start with a practice exercise. So practice exercise. Okay, so you roll a pair of dice, you roll 2 dice, and there's a first roll and a second roll, and you win if the first roll is less than the second roll. Okay, so roll 2 dice and win if, first roll is less than second roll. Okay, and so then the question is, what are your chances of winning? So use this mechanical approach we discussed to compute the probability to win. Probability to win equals. Okay, so I'll give you a couple of seconds, pause the video. 1, 2, 3, 4, 5. Okay, now if you're coming back and you computed the probability as 5/12, fantastic. You've mastered this mechanical approach to computing probabilities. If you're here just for the ride, well, the first roll in a pair of dice rolls is less than the second with probability 5/12. If you didn't get that, then look up the exercise in the book, see how we solved it, see what you did wrong, and try to get as much practice as you can, because probability is very counterintuitive. Okay? And we're going to do a couple of examples which illustrate how counterintuitive probability is. Okay? We're going to start with a game show that was called Let's Make a Deal. Okay, it aired in the 60s, 70s, and 80s. Okay, and it involves a host, Monty Hall, so sometimes it's called the Monty Hall problem, and a column in the New York Times called Ask Marilyn. Okay, and we'll see how all these things tie in together when I tell you about the game. So, the game concerns 3 doors. So there are 3 doors. Let's label them door 1, door 2, and door 3. Okay, and the game proceeds. The game show proceeds as follows. There's the contestant, and the contestant stands in front of door 1. So the contestant in front of door 1. Okay. Now the game proceeds as follows. A prize is placed randomly behind one of the doors. Okay. Prize placed randomly behind a door. So the prize could be either behind door 1, 2, or 3. Okay. Now this is where it gets tricky. Now, the host, Monty, will come and open one of the other doors, not the door the contestant is in front of. Will open one of the other doors, and it must be the case that the prize is not behind one of the other doors that are opened. So the door that's opened will not contain a prize. So Monty opens a door with no prize. Now in the game, I believe the doors with no prize had goats. Okay, so 2 goats and 1 prize, and the goal of the contestant is obviously to get the prize, because you can't really do much with a goat these days. Okay. Now you might ask, what happens if the prize is behind door 1? Then Monty has a choice of doors to open, okay, and he picks randomly. Okay. Now, let's imagine that Monty opens door, let's say door 3. Okay. So now Monty gives the contestant a choice, because door 3 has a goat, so there are 2 options for where the prize can be, and Monty asks the contestant, do you want to switch? And now, very often on the show, the contestant looks at Monty, very suspiciously, thinking that Monty is trying to get the contestant to switch, to sort of, move the contestant away from the prize that is behind door 1. And many contestants don't switch. So someone wrote into Marilyn's column, Asked Marilyn, and asked her, Marilyn was savant, supposedly the person with a very, very, very high or highest intelligence, should I switch or not? That was the question posed to Marilyn. And Marilyn said in the column, you should switch, and it's twice as likely for you to win if you switch. And then there was a huge, set of responses, even by mathematicians, who said, this is all nonsense, you're failing to educate the public correctly. Look, there are clearly 2 doors, and your chances are 1 in 2 if you stay, and 1 in 2 if you switch, and so it doesn't matter whether you switch or not. So let's analyze this game, and we'll prove that Marilyn was right, and everyone else who disagreed was wrong. Okay, so here's how we're going to prove it. And we're just going to use our mechanical, framework for computing probabilities. So the start of the experiment has the contestant behind door 1. Okay, and now the prize is placed behind one of the doors randomly. So the first step is we have to consider all possible outcomes. Okay, so what are the outcomes? The prize can be either behind door 1, or behind door 2, or behind door 3. Okay. Now, once the position of the prize is chosen. Now the next step in the game takes place, and Monty opens a door which has no prize. So if the prize is behind door 1, Monty has a choice of which doors to open. So Monty can open either door 2 or door 3. Okay? And if the prize is behind door 2, then Monty has no choice, because Monty has to open a door that has no prize, so he has to open door 3. So he has to open door 3. So this you can think of, where's the prize? Okay, and this you can think of as, what does Monty do? Monty opens. Okay, and if the prize is behind door 3, contestant is in front of door 1, so Monty has to open door 2. So this is interesting. So if the prize is behind door 1, there are 2 possible ways in which the experiment can continue. But if the prize is behind door 2 or door 3, there's only one possible way in which the experiment can continue. Now we can label these, leaves, these final outcomes, as door 1, prize behind door 1, Monty opens door 2. So we can label this 1, 2. Behind door 1, open door 3, 1, 3. Behind door 2, open door 3, 2, 3. Behind door 3, open door 2, 3, 2. Okay, so these are the possible outcomes. Possible, and if we asked you to compute the number of possible outcomes, there are 4. Okay, but now when we're computing probabilities, we need to compute the probabilities of the outcomes. Okay? And to do so, we compute the probabilities of each partial outcome and each outcome from each partial outcome and so on by adding edge probabilities. So these edges, because you choose randomly from among 3 choices, okay, the edge probabilities are 1/3. Okay, here you choose randomly from among 2 choices. Okay, so half of the time you go this way, half of the time you go that way. This corresponds to 1/3 of the time, 1/3 of the time, 1/3 of the time. So 1/2 of the time, 1/2 of the time. And here, all the time, if you get to this point where the prize is behind door 2, all the time the door 3 is open. So all the time corresponds to a probability of 1. Okay, and here all the time door 2 is open. So all the time corresponds to a probability of 1. Okay, so now we compute outcome probabilities, which correspond to what fraction of the time does this outcome occur. It's half the time of 1/3 of the time. So that's where we multiply 1/2 times 1/3. So we get 1/6. Okay, half the time of 1/3 of the time, multiply 1/6. Okay, all the time of 1/3, so 1/3. 1 times 1/3, 1 times 1/3. Okay. You can interpret this as 1/6 of the time. When you run this experiment, the outcome will be prize behind door 1, Monty opens door 2, host opens door 2. Okay, and so this is the mechanical probabilistic specification of the experiment, where what's important are the outcomes and their associated probabilities. Now we ask our question. Okay, and what's our question? Okay, what are our chances of winning if we switch? Chances of winning if we switch. Okay, question mark. Okay. So we go back to our outcomes and look at in which outcomes do we win by switching. So if the prize is behind door 1, you cannot win by switching. You lose by switching. If the prize is behind door 2, then you'll switch to door 3 and win. If the prize is behind door 3, then you'll switch to door 2 and win. So in these outcomes, you win by switching. Okay, and that's the key. We ask a question and then we identify the outcomes which correspond to that question. And in this case, we define the event of interest. The event is the outcomes 2, 3 and 3, 2. So I want to emphasize that the event, or the event of interest, is a subset of all the outcomes. It's a set of outcomes. Now we can compute the probability for this event occurring, which corresponds to the probability to win if you switch. So the probability of the event occurring is the probability to win if you switch. Okay, so now this big P means probability. Okay? And we just add up the probabilities in each outcome. So this has a probability 1/3, this has a probability 1/3. Okay, and so you get 1/3 plus 1/3, which is 2/3. Okay, the probability to win by staying is the opposite outcomes, the complement outcomes. Okay, and the complement outcomes have some 1/3. So the probability to win by staying is equal to 1/6 plus 1/6, which is 1/3. Now we could have figured that out by actually looking at the answer we already got. You win if you switch with probability 2/3. Okay, so you win by doing the opposite. The complement okay, with probability 1 minus of that, because the probabilities must add up to 1. You either win by switching or you win by staying. So the total sum has to be 100%, i.e. the probability to win by staying has to be 1 minus of this, which is 1/3. No surprise. Okay, now why did this cause so much contention? Because the intuitive argument is, well, you have two choices, okay? And so if you stay, your chances are 1 in 2, and if you switch, your chances are 1 in 2. The point is that this second choice, this other door that the host didn't open, is more likely to contain the prize than the door that you are behind. And sort of one way to view that is, you have 3 doors: door 1, door 2, door 3. Okay, and the prize is equally likely to be behind each door. Okay, and the strategy of winning by switching wins whenever the prize is behind one of these doors. Either of those doors works for winning by switching, and there are 2 out of 3 doors that you can win by switching. And so the chances are 2 out of 3 doors to win by switching. And that's just because the prize is placed has equal chances to be behind each door. Okay? And the way the game is structured is such that if you switch, you basically win whenever the prize is behind door 2 or door 3. Because Monty will have to pinpoint that to you by opening the other door. So you win whenever the prize is behind door 2 or door 3. And that happens 2 out of 3 times. You win by staying only when the prize is behind door 1, which is 1 out of 3 times. Okay? So if you want to perform an intuitive analysis, this is the correct intuitive analysis. Okay, but like I said, probability is very counterintuitive. So it's always safest to go to to go through the full mechanical route and get the answer. Okay, and now we're going to see something really strange. Okay, and that underlines why it's very important to always use the mechanical route to compute probability. So what is this thing that's really strange? Okay, so I want to show you that when games involve chance and probability, it's possible that you will prefer one game, okay, to another. You will prefer another game to a third, and then you will prefer the third game to the first. So it's kind of like a non-transitive behavior. And let me illustrate with dice. Okay, so this is I'm going to call this non-transitive dice. Okay, so non-transitive dice. And we'll do this example carefully. Okay? And you can think of this as, a game that you could play with your roommate friend who's a history major and make lots of money off them. Okay? And here's how the game goes. Okay? So I'm going to give you 3 dice. They're 3-sided dice. Okay, so die A, die B, and die C. And maybe if we were in the live version of the class, if you had answered some question correctly, I might have even given you some of these dice. Okay. So die A, it has 3 faces, so it's a 3-sided dice, and the faces are, if I draw the dice 2, 6, and 7. Okay, so think of 3 die faces. So this is 2. That's 2, 6, and 7. Okay. And die B similarly has 3 die faces. 1, 5, and 9. Okay, so that's die B, 1, 5, and 9. And die C has also 3 die faces. Okay, and the faces are 3, 4, and 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 3, 4, and 8. Okay, so you might wonder, well, okay, good. First thing you might be wondering is, how do you construct a die with 3 faces? Well, you can take a sphere and chop off 3 parts, and whenever you roll it, it's equally likely to land on each part. Or, more simply, you take a standard 6-sided die and just add, and replicate the faces. Okay. So now in a standard 6-sided die, you could replicate the faces and have two faces with 2 dots, two faces with 6 dots, and two faces with 7 dots. Okay. So that's one easy way to create a die with 3 faces. But okay, so for the moment we have 3-faced dies. So here's what you can do. You can take a friend and you can say, here's the game we're going to play. You pick a die, whatever die you want, and I pick a die, okay, and then we roll, and whoever gets the higher number wins. And your friend, because your friend is a history major, is never going to trust you and say, no way, I'm not playing. You know too much probability for me. So you say, well, listen, we can play this game for a while, and if you think that I have the better dice, okay, then you can switch any number of times. So we'll play the number of times. Okay, you can switch any number of times. And so the friend now looks at you and says, okay, that sounds reasonable. Because if I can't analyze probability, but I can see what die you picked, and then we'll play a few times. If I'm losing, I'll pick your die. I'll switch dice with you. Okay, and so let's analyze this game, and I'm going to show you something very counterintuitive that can happen when you do probabilistic analyses. Okay, it's not like deterministically, if I can beat you and you can beat John, then I can beat John. Okay, that's sort of like how things are with, let's say, tennis. But even in a game like tennis, that may not be the case, because I know how to exploit, your weakness, and you know how to exploit John's weakness, but you don't know how to exploit my weakness. But John knows how to exploit my weakness. So even, games like tennis are non-transitive, and the same thing is going to occur here. Okay, so let's see what happens. Okay, let's consider who wins between, a war that occurs between die A and die B. So which die wins? Die A versus die B. Okay. So we roll both die. Okay, die A rolls and die B rolls, and if die A is rolled a higher number than die B, then die A wins. Okay. And so we just use the mechanical approach. So here's what happens. Okay, so you have the start of the experiment. Now you roll die A. Okay, what are the outcomes for die A? Die A can either be 2, 6, or 7. Okay. And then, we roll die B. And what are the outcomes for die B? Die B can be either 1, 5, or 9. 1, 5, or 9. 1, 5, or 9. 1, 5, or 9. Okay. So if I asked you how many outcomes are possible, you would take the product rule. 3 times 3. 3 times 3. 9. Okay. But now we're doing probability. So we need to assign for each of these outcomes, let's assign a name and a probability. So the name, we can just call this name, 1, 2. This is, 2, 1. 2, 5. 2, 9. Okay, 6, 1. 6, 5. And 6, 9. Okay, and then 7, 1. 7, 5. And then 7, 9. Okay, and now let's assign probabilities. Well, we compute the partial outcome probabilities and then the probability. Basically, we add probabilities to the edges. So 1/3, 1/3, 1/3. Why 1/3? Because there are 3 outcomes and each of them is equally likely. Then 1/3, 1/3, 1/3. Again, 3 outcomes each equally likely. 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. Okay, and now 1/3 of the time this outcome occurs. So product rule, 1/9 of the time. 1/3, 1/3, 1/9, 1/9. Okay, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. But they're all 1/3 times 1/3, so 1/9 for all of them. This is a very special kind of set of probabilities. See, notice they're all the same. Okay, we will see later. We call this a uniform probability space, but that's notation. Okay. We've computed probabilities. Now let's ask our question. Okay. When does die A beat die B? When does die A win? When does die A win? Okay, so that's our question. And so let's answer our question. Well, we need to identify the outcomes where die A wins. And it's not too hard to sort of identify those outcomes. Let me box them. So here, 1. 2, 5, 2, 9, die A loses. 6, 1, 6, 5, die A wins. So 2, 3, okay, and then 6, 9, die A loses. 7, 1, 7, 5, win, win. Win, win. Okay. and 7, 9 losers. Okay, so what's the event of interest? The event that is going to help us to compute this probability, it's just these red outcomes. So the event of interest that corresponds to that question is 2, 1, 6, 1, 6, 5, 7, 1, and 7, 5. Okay? Those are the outcomes. They all have a probability 1/9. So now we're going quickly, the probability of that event, which is the sum of the outcome probabilities, so the probability of this event. But since they're all 1/9, the probability is just the number of outcomes divided by 9. It's just 5 over 9. Boom. So die A beats die B more often than not. So we will say that die A beats die B. Okay, so now I'm going to give you more practice. Do the battle between die B versus die C. Okay, die B versus die C. What's the probability that B wins? Probability that B wins. Okay, and then die C versus die B. What's the probability that C wins? Oh, die C versus die A, sorry. So then that's all three battles, A versus B, B versus C, C versus A. Okay. So pause the video, take as much time as you want to compute these. Good practice, okay? And I'll give you 1, 2, 3 seconds. And now if you're coming back just for the ride, or if you computed that the probability that B wins the battle versus C is 5/9, and the probability that C wins the battle versus A is 5/9, and you did it right. Well done. You're really understanding the mechanical approach to computing probabilities. Fantastic. Okay, but now we see what's the dilemma. So die B beats die C, and die C beats die A. So no matter what die your friend chose, let's say that your friend chose die B, you pick A. If they chose C, you pick B. If they chose A, you pick C. So having the option to go second in picking is a huge advantage here. You'll win, more than 50% of the battles. And if you're gambling on this, you'll win a lot of money, especially if you play 1,000 battles. Okay? So, this is non-transitive die. Very weird phenomenon. Die A beats B, B beats C, C beats A. This is something that can happen when probabilities are involved. That's why probabilities are so counterintuitive. Okay, so let's erase. And now sort of discuss the formal, footing of probability theory, which is called a probability space. Okay, and we'll list these sort of experiments that we discuss in the language of the probability space. Speed erase. Let's go fast. Bam.